Okay, hello everybody. I'm just going to do a really quick video here on section 14.2 of the textbook, the introduction to the solutions chapter. This is going to be on your exam Tuesday. We need to just barely start 14 so that we can stay on track for the summer semester. So I'm going to jump into the slides and I'll go over just that one initial section there, 14.2. Okay, there we go. So talking about solutions, we have homogeneous mixtures, so they're uniform throughout. If I have a glass of this solution, regardless if I sample from the top of the glass or the middle or the bottom, I should see the same ratio of solvent to solute or solutes. Again, the solvent is going to be the majority component of that solution, and the solute or solutes are the minority components. So if we have salt water, the water would be the solvent and the salt. The sodium chloride would be the solute. We have this tendency towards spontaneous mixing, so just leaving things by themselves, we should see that uniformity occur. If I added salt to water as it dissolves, so long as it actually dissolves, I shouldn't have this region with all the salt in it and then this other region that's pure water. Or you can see this example here. If we have this container, we're able to introduce a barrier that prevents the water from one side mixing with the other. If I add the salt to one side, it'll dissolve. But as soon as I remove that barrier, it's going to spontaneously mix. The sodium chloride atoms or ions on one side are going to spontaneously move over to the other side and mix. They're not just going to stay segregated to one section there. Okay, so common types of solutions. Solution, again, just needs a solute and a solvent. And there's all kinds of different types of solutions. We can dissolve, liquids in liquids, solids in liquids. We can also dissolve gases into liquids. So soda is an example of a solution where I have a gas, CO2, dissolved in a liquid. So all solutions aren't necessarily just liquids, and they don't always just involve a solid going into a liquid. We can have gaseous solutions. The air is a solution. Nitrogen is the majority component, makes about 79–80% of the air. So that would be considered the solvent. Oxygen makes up, around 19–20% of the air. So that would be one of your solutes. And then you also have small trace amounts of argon, of water, of CO2. So those would also be solutes in that mixture. Solutions can even be solids. All of our alloys are technically solutions. Brass is one of the examples they give. So that's a solid, but it's a mixture. It's a mixture of multiple different metals, the majority component usually being copper. So in that case, that would be our solvent. And zinc or tin or other things being the minority components, they would be the solutes in that mixture, or that solution in this case. There's an example, of gases dissolved in a liquid. That's one type of solution. Okay, so if something is noticeably soluble, if we can dissolve a significant amount of it, we would say that it is soluble. And we're going to treat sort of those like dissolves like rules to this. And if for the most part, we can't really dissolve any of this or very, very, very little of this into something, then it would be what we would call insoluble. And those are usually things that are dissimilar, like they said, oil and water, where I have something nonpolar and something polar. So it depends on the type of intermolecular attractive forces and also that tendency towards mixing, that desire to form that homogeneous mixture, or what we're going to see in a little bit is known as entropy. So entropy tends towards disorder. So you could think about, we're an example of entropy. We have to continually put energy into our body to prevent it from breaking down. So you always have to keep eating food to replace your cells, to regenerate yourself, to give yourself energy to move around. If you don't do that, if you don't continually invest energy in that, just by the rules of entropy, you're going to start to break down. Or you could think about if I take a watch and I break it and I put it in a bag or in a hat or whatever, that watch isn't going to spontaneously reassemble. It's always going to tend towards a lower potential energy. The same thing is true when we mix. If we have this example, this container with neon and argon contained within it, again, we have a barrier that prevents them from interacting with each other. If we remove the barrier, it's going to be a lower potential energy for those things to mix and form a homogeneous mixture and be uniform across. And that's lowers the potential energy and tends towards entropy. So a lot of times when we dissolve something, if we create a solution, by adding that solute into there, we're actually going to lower the potential energy by dissolving it, or we're going to have that increase in entropy. And that's one of the things that actually helps these things to dissolve and is why something is soluble and why we get that homogeneous mixture and that lowering of potential energy. So which statement is true? Ideal gases mix because mixing decreases their potential energy. Ideal gases mix because mixing increases their potential energy. Ideal gases mix because mixing decreases their entropy, or it mixes because it increases their entropy. Here we can see it increases their entropy and also should technically decrease the overall potential energy within that container. To see intermolecular attractive forces, how they come into play when something's dissolved. Whatever the solute is, it technically becomes what we would call solvated, or it becomes surrounded spherically in 3 dimensions by whatever those solvent molecules are. So we have to have some sort of interaction. So here we have 2 nonpolar molecules. They only have dispersion forces. So we could see, if heptane was our solvent and pentane was our solute, what I would do is I'd have that pentane molecule, and as it goes into solution, the reason it would dissolve is it would become surrounded by heptane molecules, and they would have the same intermolecular attractive forces. They would have those dispersion forces interacting around it, and that would solvate that, and that would go into solution. Same thing's true if I have things that both have dipoles or polar, hydrogen bonding, and ion dipole. If I dissolve that ion, the reason that it dissociates is so that the positive component and the negative component can have a solvation sphere, in this case of water molecules, around it. So what we have to do when we dissolve something is we have to think about what forces are we breaking, or what forces do we have to divest from each other, and what new forces are we making, and how does that affect the overall potential energy that's present there. So if I'm going to dissolve something, if I have a pure solvent, if I have water, then all my interactions are between water molecule 1 and water molecule 2, etc. So what I have to do is break those solvent-solvent interactions. So those intermolecular forces, some amount of energy is going to have to go in to separate some of those water molecules from each other. And the same is true for the solute. If I have sugar, if I have a cube of sugar, that's a molecular solid. There's intermolecular attractive forces between each sugar molecule. If that goes into a solution, I have to have enough energy actually to break those intermolecular attractive forces between one sugar molecule and another. So that's going to be the energy investment. That's going to be sort of the the endothermic portion of this process. But then when I form the solution, I'm going to get a new interaction, and that's going to be what are the attractive forces between the solvent and the solute. So what does that look like when the sugar molecule comes to the water and they interact? And that's going to release a certain amount of energy. So depending on the energy that goes in and the energy that's released, we can get something to dissolve and potentially still have a lower potential energy now with that new solution. Now here's an example. Here you can see if the solvent-solute interactions, so the new interactions, are greater than the amount of energy it took to break the solvent-solvent interactions and the solute-solute interactions, then a solution should form. If those interactions are equal, due to the tendency of mixing, due to entropy, we should still see that solution form. If the solvent-solute interactions are actually weaker than the original solvent-solvent interactions and solute-solute interactions, then usually we won't see that solution form, unless the difference is small, and then the entropy of forming the solution may make up that difference. So it is possible that the solute-solvent interactions are weaker than the solvent-solvent and solute-solute interactions, but that we would still form a solution. So yep, we must overcome all the solute-solute attractive forces and at least some of the solvent-solvent attractive forces. Because the solvent is the majority component, if I have water and I'm dissolving sugar in water, I'm not separating every single water molecule. There's a lot in there. I just have to separate enough so that I can form those solvation spheres around each one of those sugar molecules. And like it says, both of these processes are endothermic. We do have to put energy in, energy investment to separate or to break those intermolecular attractive forces. And then forming those new bonds or those new interactions should be exothermic. So as that puts out energy, that's going to help drive the previous portion where we're weakening those solvent-solvent, solute-solute interactions. Okay, so maximum solubility can be determined by what's going on, what are the interactions there, do we have like dissolving like or not. As it says, gases are always soluble in each other, and liquids should be miscible if they're very similar in terms of their polarity and their intermolecular attractive forces. Alcohol and water, both polar, both have hydrogen bonding, they would be miscible, or we could dissolve one in the other. Oil and water, one's nonpolar, the other's polar, so these are immiscible, or they will not dissolve in the other. And these are also affected by temperature and pressure. If we alter the temperature, we're putting more energy into this thing, or if we're lowering it, we're giving it less energy. So that's going to affect how much energy is available to break those intermolecular attractive forces. And with the pressure, we're also controlling how tightly are those things brought together, or how little force is there, I guess, to bring them together or keep them together. Okay, so will it dissolve? Like I said, the rule, like dissolves like. You've heard me say that multiple times. If the solvent-solute interactions in a mixture are comparable in strength to the solvent-solvent interactions and the solute-solute interactions, what can you conclude about solutions formed in this mixture? So solvent-solute interactions are similar, then the ones we have to break, so the energy or the bonds we're going to form, or the attractive forces we form are similar to the ones we're going to have to break, then the homogeneous solution should form. Due to the increased entropy of them mixing, that's going to be more than enough to cover that equality there. Consider the table listing the solubilities of several alcohols in water, and in hexane, which statement best describes the observed trend in terms of intermolecular attractive forces. So if you believe they're talking about this table, so several alcohols in water, so starting with methanol, ethanol, 2 carbons, propanol 3, butanol 4, pentanol 5, you can see the solubility starts to decrease. So as you move down the list, molecules become more polar, less soluble in water, more soluble in hexane. As you move down the list, they become more polar, more soluble in water, and less soluble in hexane. As you move down the list, the molecules become less polar, therefore less soluble in water, more soluble in hexane. As you move down the list, they become less polar, more soluble in water, and less soluble in hexane. And should be, as you move down the list, they become less polar. You have a longer and longer non-polar carbon chain, so that hydrogen bonding, the polarity on that one end of the molecule, becomes less and less noticeable the longer that chain gets. So with the shorter chains, with methanol, ethanol, propanol, you're very soluble, and then your solubility starts to decrease. And there's a greater likelihood of it, or more, becoming more and more soluble in less polar substances like hexane. Okay, so that's all it is. Like I said, not very much. After the exam on Wednesday, we're going to start on section 14.3, looking at those specific enthalpies that are actually involved there in terms of breaking those solute-solute interactions, solvent-solvent interactions, and forming the solvent-solute interactions. So hopefully this was helpful. Hopefully studying's going well. I'm going to wrap up the video here, and I'll see you Tuesday for the exam.